Today I am discussing about quantum statistics and different type of statistics. The main features of quantum statistics. First of all, we will discuss about Bose-Einstein statistics. The particles are identical and indistinguishable. They have zero or integral spin. These particles are called bosons. Bosons do not obey Pauli's exclusion principle. Examples: photons, alpha particles. The wave functions are symmetric. Second one is FD statistics or Fermi-Dirac statistics. The particles are identical and indistinguishable. They have odd half integral spin. These particles are called fermions. They obey Pauli's exclusion principle. Their wave functions are antisymmetric. Example: electrons, protons and neutrons. Pictorial comparison of three statistics. Consider two particles, say A and B, and we have two cells to be occupied. Here in classical statics, the particles can be arranged in four possible states. That is, in each box we can arrange particles in four ways. Here I am showing how it is arranged in two boxes. In Bose-Einstein statistics, if the two particles are indistinguishable, we have three possible states of the system. In FD statistics, they obey Pauli's exclusion principle, so we have only one arrangement is possible. Indistinguishability of identical particles. The particles contained in a system can be classified into two types: distinguishable particle and indistinguishable particle. Distinguishable particle means which are dissimilar, no restriction for number of particles in an energy state, do not consider the spin of the particle, or these will obey Maxwell-Boltzmann statistics provided the de Broglie wavelength of the particle is less than the mean distance between the particles. Indistinguishable particles are similar. Example: electrons, neutrons and protons. Their properties are like a charge, mass, spin, angular momentum are same for each of the particle. They are indistinguishable. The two type of statistics are applicable. They are Bose-Einstein and FD statistics. When the position and spin coordinates of two particles are interchanged, if there is no physical way of measuring that change has been made, then the particles are said to be indistinguishable. More about indistinguishability. Consider a system containing n identical particles occupying a volume V. In classical mechanics, we can determine Qi and Pi simultaneously and accurately, but in quantum mechanics it is not possible. Let P average denote the average momentum of a molecule in the gas, and let the intermolecular separation be R average. By classically, R dot P very much greater than H, where H is the Planck's constant. That is, the de Broglie wavelength lambda is equals H by P. Hence, R average is very much greater than H by P average. That is, R average is very much greater than lambda average. Under this condition, the wave functions do not overlap and hence the particles can be distinguished. That is, R average very much less than lambda average. Under this condition, the wave functions of one particle overlaps the other. The particles are indistinguishable. That is, R average very much greater than lambda average. It is the limit up to which classical mechanics can be applied. Let us assume that each particle of the system occupies a very small cube outside R. Then if V is the volume of n molecules, then R cube into n equals V. That is, R average equals V by n raised to 1 by 3. Let E be the average energy at a temperature T. E equals P square by 2m equals 3 by 2 kT. That is, P average equals 3m kT raised to 1 by 2. That is, lambda average equals H by 3m kT raised to half. Substitute for R average and lambda average in equation A, that is, P by n raised to 1 by 3 very much greater than H by 3m kT raised to half. This equation shows that classical mechanics can be applied only when n is small, T is high, m is not small. Thank you.